So a basic overview of computing derivatives. So we learned a bunch of basic derivatives, and all of these we can prove with either our definition of the derivative or by modifying ones that we know, like deriving the cotangent, knowing the derivative of tangent. But once we've proven all of them, we can just use them. So we'll go down the list. We know that the derivative of a polynomial is just multiply and subtract 1 from the power. So if you have x to the 5th, that would just be 5x to the 4th. So just multiply, drop the power down. We like polynomials. We can take the derivative of e to the x, and notice this is an exponential function where the x is up in the exponent. So different than the polynomial, you're not going to multiply by x and drop 1 from the power, it's different. So the derivative of e to the x is just e to the x. My dad used to quiz me on that one all the time when I was like 10. He'd be like, what's the derivative of e to the x? I'm like, 0, 1, I don't know. Yeah, derivative of e to the x is just e to the x. Derivative of a to the x, where a is just some random constant, not as special as e, you end up just taking a to the x and multiplying by the ln of a. And again, all of these can be proven. We'll do them in separate videos, but for now, we're just writing them so that we can use them. Derivative of ln of x happens to be 1 over x. The derivative of log with a base not quite as special as log base e is still 1 over x, but then you have to divide by that little ln of a, just a part of a change of base formula, that sort of thing. Now we got all our trig functions. Derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of tangent is secant squared. And then the derivative of cotangent is just the co-counterpart of this. So the co's are all negative. So derivative of cotangent is negative, and then cosecant squared of x. Derivative of secant is just secant x tangent x. And then the derivative of cosecant is the negative co-counterpart of this thing. So negative cosecant x cotangent x. So again, it looks like a lot, but if you know those three, you can kind of figure out what the other ones are. Awesome. So these are all like your set functions. Or we could do combinations. So shout out if anyone thinks of Terminator when you think of that line. But anyway, so we can do combinations because it would just be too easy if they just gave us these straight functions. That would be it. So we can multiply functions together. We could divide some of these functions. We could put functions inside of functions. So like if any of these x's were instead of an x, it was sine x. That would be your chain rule, compositions of functions, functions within other functions. So like this thing here that I have lined up, I have the tangent not just of an x, but the tangent of ln of x. So that'll be my chain rule where I take the derivative of the, I usually like to write outside first then inside, although obviously it doesn't matter because it's all commutative, but I usually like to work from the outside in. Again, commutative, doesn't matter, but so we're going to do lots of examples of these coming up, but I'll just walk you through a couple now. So we're looking at this guy here, x cubed times sine of x. Hey, I've got two functions multiplying together. Maybe I'll use product rule. So my product rule, I wrote it out very non-mathy here, but you can find it mathy in the notes. But basically you're taking the first times the derivative of the second plus the second times the derivative of the first. Everything is commutative here, so it doesn't really matter what order you like to do it. That's the way my teacher told me, so that's the way that sticks. But if you like taking the derivative of the first and leaving the second alone, that's okay too. As long as in one part you take the derivative of one of the functions and leave the other alone, and then add, reverse it. So I'll do it in the order I have here. I'll leave the first alone, and then take the derivative of the second guy. Oops. Yeah, leave the first alone. Take the derivative of the second. I'm looking at sine x. The derivative of sine x is cosine x. And then plus, leave the second guy alone. Then take the derivative of the first guy. So the derivative of x cubed is polynomial, so it's just 3x squared. Multiply and drop the power down. And you could clean that up if you wanted, but that's the gist. You could just throw that 3x squared first, is probably all I would do. and you'd end up with that nice shiny answer. Cool. Let's do it again. So here again we have a product. We have x to the fourth times the tangent of ln of x. So that's what's going on the outset. So I see two things multiplied together. I want to use my product rule. So again, maybe I'll do a different order this time. Maybe I'll take the derivative of this first guy first. So 4x cubed, take the derivative of one of them, leave the other guy alone, don't touch it, and then plus reverse. Leave the first guy alone now, take the derivative of the second. So, this second function is the tangent, not just the tangent of x, it's the tangent of the ln of x. So whenever you have that function inside another function, that's your key to do chain rule. So chain rule says take the derivative of the outside function first. So the derivative of tangent is secant squared. So secant squared, leave that inside alone. And then take the derivative of the inside. So the derivative of the ln of x is 1 over x. And again, you could clean that up a bit if you wanted to. Maybe just, I don't know, not a lot we can do. Just cancel out one of those x's and leave it there. And so we'll do a bunch of examples just to get the hang of it, but that's all it is, just a bunch of base functions and their derivatives and a bunch of ways of combining them. And there you go.